let me first, before we get into the algebra, the small amount of algebra that is required to prove this particular result, let me discuss a little notational thing. Why k and not n? Why have I been talking about p of k when at first I was using the letter n, saying what we want to prove is for all n, 7 to the n minus 2 to the n is an odd multiple of 5. And it's a subtle thing. You don't have to use a different letter, but it's a subtle logical thing. We're trying to reflect a subtle logical thing. Here's the correct thing that we're trying to do. We're trying to show that for every positive integer, every natural number, we're going to say those are synonymous, if I know that this statement is true for that natural number, then I know it for the next one. So notice that what I'm saying is that for every natural number, then the next thing is an if. If I know it for p of k, then I know it for p of k plus 1. So what we're going to do in a minute is we're going to pick an arbitrary, unspecified k, but just one at a time, and assume that p of k is true, and just try to get to the next one. Really important that we're not going to assume that they're all true. Okay, that would be false. If I said the next thing I was going to do in the inductive step of the proof was assume that p of n is true for all positive integers n all at once, then that's what I'm trying to prove. That would be utterly circular reasoning. And induction can seem circular because this is a very subtle distinction between these two statements. So what we're showing is that for every natural number, if I happen to just know that one at a time, then I can get to the next one, and that's all I need to show. If that works no matter what that one was, then I can start this chain p of 1 and plus p of 2 and plus p of 3, etc. It goes on forever. So it's not going to be circular reasoning, but it's a subtle distinction, and the k is to help us distinguish between those two statements. We're only going to switch back to the letter n when we can really say, yeah, we really actually know they're all true for all n. That is what we've proved. But we're not going to assume that because that would be utterly false. Okay, so here's how we're going to write the inductive step then. So we're going to make clear that we're doing an inductive step, because otherwise it could seem circular. We're going to assume that 7 to the k minus 2 to the k is an odd multiple of 5. Okay, and now to show, this is a subproof that we want to do. Given that extra assumption that we didn't have before, I want to show for this particular k, same thing is true for k plus 1. So this is p of k, that's p of k plus 1. So now we're just getting down to cases here. Okay, so that's a nice way to sort of start an argument. For 7 to the k plus 1 minus 2 to the k plus 1. Here's the crucial thing. Well, there's two crucial pieces, I think, but the most crucial piece is that 7 to the k plus 1 is defined in terms of 7 to the k. You might not think of it that way, but it really is. This is repeated multiplication that says multiply 7 by itself k plus 1 times. If somebody had already multiplied 7 by itself 241 times and then asks you to do it 242 times, you're not going to start over from the start. You're going to ask her, what was it multiplied 241 times? And then just multiply one more 7. So it's helpful to think about it in terms of these very particular cases sometimes, and without too many variables. So that's why I like to think about it. So this is 7 to the k times 7 minus 2 to the k times 2. Okay, so that would look better here. That already gets this in there almost. Ooh, but it's not just 7 to the k minus 2 to the k. So here we have to do a very common little mathematical trick, which is add and subtract the same thing. Okay, I need to get to where the 7 to the k and the 2 to the k are both multiplied by the same common factor, and they're not multiplied by the same common factor. So this is part that's not super obvious, I think. A lot of people would get stuck right here. Okay, I just subtracted and added exactly the same thing. So this is the same thing, but how does this groups in a very nice way? This is 7 to the k times 7 minus 2. Ah, okay. Okay. Notice what 7 minus 2 is. Plus 7 to the k minus 2 to the k all times 2. Aha. Okay. So this is really, we're almost home free here. We've got the quantity we wanted to analyze, in terms of exactly the quantity we're allowed to assume something about. Okay, so now this, I'm going to need more room. Okay, I've unfortunately this erased my assumption, but remember we're assuming that this is an odd multiple of 5. Okay, well, so this is an even multiple of 5. So this is a multiple of 5. We're not using actually that's odd right here. Um, that's a multiple of 5. Then multiply that by 2, you're going to get an even multiple of 5. And then this is an odd number, 7 in the case, certainly odd, times 5, so that's an odd multiple of 5. So this is an odd multiple of 5 plus an even multiple of 5. You know, we call that, probably a better way to say that is a multiple of 10. In other words, it's going to end with a 0. Okay, so that's going to end with a 0, and this is really using the inductive hypothesis. I'm assuming that somebody's checked for like k equals 231 that this really ended in a 5. And then that's going to imply that the next one's going to end in a 5 as well. Okay, so the total is also an odd multiple of 5. I'm jumping the gun a little bit in terms of the book's sequence of things, but I've done this before where we talk about divisibility. We're going to talk very precisely about how divisibility works and be really, really careful about it, mainly as practice and being careful and when we get to the really tricky stuff where it's not at all obvious. But for right now, let's assume we know things like, yeah, if you add an odd multiple of 5 to a multiple of 10, you get an odd multiple of 5. Okay, so that is statement P of k plus 1. So we've shown that P of k implies P of k plus 1 for every k. That's the inductive step. We also showed that P of 1 was true. That's the base case. Base case plus inductive step shows the whole thing. And then to probably just to be nice and clear and to have good style, we would say hence or therefore by induction. And now we bring the n back. 7 to the n minus 2 to the n is an odd multiple of 5 for all n in n, the natural numbers or the positive integers. Okay, so that's an example of a careful proof by mathematical induction.